so we often have to solve an inverse problem, right? Where we have observations and we have a model and we want to figure out what the input parameters are. So we have to do this very frequently. And the assertion that I'll make to start with is that we've been doing it wrong. We've been doing it wrong for a very long time because we've been using mathematical techniques to give us exactly the opposite of what we want. We've been using techniques that give us solutions that smear out everything that's interesting. And what I mean by that will become clear as we go through what will hopefully be a very long and terribly boring talk. So in earth sciences and in most sciences, I don't really know how statisticians do things, but there are really three types of questions we want to answer. Classical scientists, we think about all of us working from first principles, coming up with the true physics of the problem, and then turning the crank and making predictions about nature. This is the type of thing that we all think scientists do a lot of the time. That's forward models. We guess at some inputs, we spend our time coming up with a model, and then we make predictions that we can test against observations. Of course, in practice, it's more complicated than that. And for the scenario I described at the beginning, where we want to do something like see the interior of the Earth, we don't know the inputs. We want to solve for the inputs. So in that case, we spend our time doing state estimation, where we guess at a model, we have some observations, and then we want to solve for the inputs to that model. We want to solve for what makes the predictions. Least squares would be a classical example of this. And then the thing that's a little bit more interesting these days is where we have inputs, we have outputs, and we're not yet clever enough to know what the model is, but we want one that works very well anyway, and so we learn for it. So a neural network, a random forest, something like that, any one of those. So the first thing I'm going to do, the first part of this talk is about solving a state estimation problem. Then the second part of this talk is going to be pretty interesting. It's going to be about how we can use a machine learning technique to actually help us with the first part of the problem. And that's a pretty fun problem. Okay, so the first part of the talk is about something called compressed sensing, or sparse state estimation. Who's heard of compressed sensing or sparse state estimation before? In statistics, who's heard of the lasso? Yeah, it's pretty much all the same thing. And to give you an idea of how popular this is, here's an n-gram from Archive. Only goes up to 2014. But what you can see here is if you search for compressed sensing, sparse recovery, it goes from nothing in about 2004 prior to that to you add these two things together, assuming they're independent, and over 1% of all papers deposited on Archive in 2014 have either sparse recovery or compressed sensing in them. So something's happening there. What is it? So we're going to go through roughly what it is first. And compressed sensing, in the simplest possible sense, is a method for solving an underdetermined system of linear equations. So this is a trivial thing to do. Conceptually, it's shown here. You have some model, you have some long state vector that you don't know, and you have some small vector for the data. So you just multiply these things together in general. What we want to do is we want to recover the solution from this. So we're dealing with systems that are underdetermined. We have more unknowns than we have data. Really pleasant case. It's what everyone hopes for in a problem. Yeah, it's totally fine. Okay, so traditionally, how would you do this? We all know how to do this. We typically solve this using something like a damped least squares approach. Here, I use kind of the notation that's used in geophysics for a linear system. I have no idea what's used here. The linear operator is typically called G, the state vector is typically called M, and the observation vector is typically called D. You want to do something like minimize the L2 norm on that, and then you damp the oscillations of the solution. This is a pretty standard formulation of what's called bridge regression. I think that's the standard term in statistics. So this is exactly what you do all the time. So it's not clear that that's the philosophically obvious thing we want to do. And one thing that we might want to do is something that's a little bit the opposite of that. Instead of damping oscillations and looking for smooth variations in the state vector, what if we wanted to do something else? What if we wanted to look for a state vector that was sparsely populated? So a state vector that was full mostly of zeros, but only had a few non-zero values. Now, if you think about this, this is a little bit interesting. Philosophically, you might want to hunt for a simple system, one that has a lot of variables that you can throw away and only a few that you'll keep. So this is a type of regression you might want to do a lot in practice. You might want to solve for a sparse system. What are the fewest number of elements I need to describe this? And so geometrically, this is what it looks like. You have some relatively dense linear operator, you have some dense data vector, but you want to solve for something that looks like this. You have a state vector that's mostly full of zeros, and then you have a couple of non-zero values. This is the central idea behind sparse recovery. Okay, so by analogy with the ridge regression case, how would you write this? Well, you do the same thing on the data, do the L1 norm into the data. But then, how do you regularize the problem? Well, following along with the description I just said, what you want to do is you want to minimize the number of non-zero values in your state vector. And so what does that mean? That means you want to look at your state vector and you want to count the number of non-zero values. And that's what this notation is meant to denote, a counting norm. So just go through your state vector and count the number of non-zero values. It's not a true norm because there's a divide by zero in there. So bear with me that I call it a norm for the time being. So how do you do that? The L0 norm is painful, right? It's not smoothly differentiable, so you can't just obviously throw it into some nice solver. It's hard to use. So the most obvious approach is simply a combinatorial one, where you just brute force through things. That's obviously not going to work when you have any relatively interesting number of parameters. It's just too expensive. So the compressed sensing revolution is essentially about changing just one number. This to that. And now you know everything you need to know about compressed sensing. So compressed sensing is largely about the idea that under some circumstances, and I'll describe what those circumstances are, they've all been discovered by statisticians, by the way. Statisticians have completely led the way on this. And it's fantastic because most of the work is computational and empirical, and it's great. So the basic idea is that under some circumstances, the L1 norm on the state vector actually recovers the same solution that you would get if you went after the problem using the L0 norm. So the L1 norm is used as a proxy for the L0 norm. And this is tremendously powerful because we sure as heck know how to solve this problem. There are whole classes of algorithms, quadratic programming algorithms, that are very good at solving this problem. So why does this work? Why does it sort of work? So here I sketch out kind of the geometry of this problem. And anyone who's, if you've ever gone on YouTube and watched Emmanuel Canda's his lectures about this stuff is very, very familiar to you. So I'm going to sketch out a problem in 3 different ways with just 3 different norms here. So we're going to look at the problem where the thing we want to minimize is this thing f here. We have the linear goodness of fit operator here, and then we have some norm here. All right. So imagine a really simple problem, a problem where you have 2 parameters that you want to fit. Okay. I call them M1 and M2. That's a pretty simple problem, right? What you would do is say, for anything here in this blue ellipse-shaped thing, you'd be any combination of values, the M1 and M2 there, give you what you would call a satisfactory fit to your data by some metric. So you're pretty happy with that. For each of these different norms, the satisfactory fit to the data is the same blue ellipse. It doesn't change, right? Those values, because this quantity doesn't change at all. However, what regularization looks like does change. So here is the shape of an L2 regularizer in 2 dimensions. It's a circle. The problem we really want to solve is this one here, where we strongly penalize a solution that isn't only on one of the axes. We strongly penalize that solution. And so this shape here is this kind of X or cross-shaped thing. And what do you know about it? It's not convex. If it's not convex, it's hard to solve. Non-convex problems are really, really, really hard. And so the thing that gets interesting is if you look at the L1 solution here, which is the minimally convex shape that we can create. If you think about solving these problems, what you do in the real world is you kind of expand your surfaces in terms of what you think is a good fit to the data. If you look at this, as you expand the L1 surface and the L0 surface, in this particular case, the intersection between the 2 is the same. The solution you would get is the same. And so this is the geometric rationale behind compressed sensing. Pardon me. This is the geometric rationale behind the idea that the L1 norm can recover the L0 pseudo-norm very frequently. So it works very well when this blue thingy is very, very far away from the origin. That tends to be the situation where it works very well. So this is the idea. And in this case, you could recover a solution where you did this, where you only had a non-zero value of this M2 variable. So it would be sparse in the sense that your state vector had a 0 and 1 non-zero value. So that's the basic idea. Okay, so this sounds pretty cool. We'll talk a little bit about how it's solved and the conditions under which this works. It does not work under all conditions.
If L0 solution, you have two solutions, right? But in L1,
Yeah, up here as well.
Yeah, right.
Yeah. Yep.
Not exactly the same.
Well, this one could be extended up as well to get the top point, but they are a little different. So this sounds cool. I showed you the archive thing, right? So this is really new. It's really exciting. Turns out it's totally not new.
You have one, you can put minimize. Right.
We can talk about uniqueness. We can talk about uniqueness in a little bit. So there's a cool historical, a whole body of interesting history here. So Gaspard de Prony, anyone heard of de Prony? He plays a big role in people who work on mechanics, because if you ever use, there's a representation of viscosity, it's called Prony series. So if you're ever modeling something viscoelastic, Prony has a huge role. Well, way back when, in 1795, Prony, he invented kind of a proto-Fourier series. And so what he did was he looked at something that roughly looked like this. It had a cosine term, and it was multiplied by a damped exponential. And so it's clearly kind of a proto-Fourier series. Not quite. Fourier came about a decade after, a little bit more. And so what he did was solve this problem, and he came up with this iterative algorithm, which you could officially call weird. And what was weird about it was that it only worked up to estimating a state vector size of about 25, and the state vector could only have about 13 non-zero values in it. So he invented this weird iterative algorithm in 1795, which we would call a compressed sensing algorithm today. It's an algorithm for recovering the L1 norm. So why didn't everyone pay attention to this? Why didn't it take over the world? Well, it turned out, in the same year, this extremely happy gentleman here, okay, I get one chuckle for that. Pretty good. Legendre, he wrote in that year, in 1795, the nice matrix vector version of least squares, which was analytically tractable. So he didn't invent it at all. These squares have been around forever. But he wrote a really compact form of it. And as I note there, it turned out to be a little bit popular because it was really, 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 really easy to do. So one of the things that turns out to be hugely interesting about compressed sensing is compressed sensing has been invented time and time and time again. But it's been forgotten time and time and time again. So I'll take you through some of the interesting history of this. In terms of how you'd actually want to solve a problem with this, and this is by no means exhaustive. This is not at all exhaustive. But in terms of things that made this happen kind of in the modern, back in the 1940s, Danzig invented the simplex algorithm. There was a Russian precursor as well, so there's some debate about the priority. But that turns out to be useful because that helps us solve problems with L1 norms. Nowadays, in the compressed sensing literature, this figure is shown a lot. It's from a 1973 paper by Claerbout and Muir. They're generally given credit for kicking off the modern sparse state recovery revolution. Claerbout was a professor at Stanford, geophysicist. Totally. Have you guys ever heard of Dave Donahoe? He's a statistician at Stanford. His undergraduate advisor was Claerbout. Supposedly. So in this paper, Claerbout proposes this. He doesn't actually say much about how to solve it, but I will tell you this. Claerbout's done a lot of consulting for the oil industry. He actually owns an island now, so I'm pretty confident that he did pretty well by this stuff. Despite the fact that people were starting to do interesting things with this, mathematicians hated this stuff. Mathematicians were totally not into it because you could prove for something like the simplex algorithm that it would take forever to converge. You could find these cases where worst case convergence just went on forever and ever and ever. So mathematicians weren't too thrilled with it. However, in practice, things got a lot more interesting in 1984 when Karmakar published his interior point method. So I'll say just a little bit, I'll wave my hands, literally wave my hands to explain how the simplex algorithm works. Who's ever used the simplex algorithm? Not the Nedler-Meade simplex algorithm in MATLAB, that's something totally different. So simplex algorithm is actually something you've probably all done in high school. So if you draw an XY plot and have a bunch of equality and inequality constraints, and you search for the region that satisfies all of them, anyone ever remember doing that in high school? That is using the simplex algorithm. It's a way of transversing effectively, efficiently, around the convex hull of a solution space. So it's a way of doing that. What Karmakar did is he sped it up radically by saying, you know what? I don't have to just transverse around the edges of these things. I can actually tunnel through the convex hull and head straight towards my solution. So in practice, this was like a really, 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 really big deal. And slowly, some of the mathematicians and statisticians started to take notice. Stanford had a huge role in this. So Chen et al., there was an early record called Atomistic Basis Pursuit that came out of Donahoe's group at Stanford, and they philosophically elucidated this very, very well in terms of searching for sparsity. We should obtain the sparsest representation of the object, the one with the fewest significant coefficients. So after you read that, you should stop me immediately, and you should say, yeah, I know what the SVD is. SVD, or PCA, eigenvalue decomposition. So I know what that is. Isn't that doing the exact same thing? Well, that is a way of reducing kind of the dimensionality of a problem, but what's distinct about the compressed centering approach and why it's found a lot of interest is people have spent a lot of time trying to interpret what their principal components or their eigenvalues actually are. What you're allowed to do here is you're allowed to compress actually in the model space that you pick. So you don't have to project it into some space that's difficult for you to comprehend. You can compress, you can find the fewest number of coefficients in a space that's very natural for your problem. And that's why it's been so interesting to a lot of people. So then we have a contribution from Tib Shirani. He formulated the problem as what we now call the lasso problem. People have heard of the lasso? So he formulated that. He's a biostatistician. He was at Toronto at the time. And then things started getting really interesting. So in 2005, Candace, Romberg, and Tao, that's Terry Tao, like the Terry Tao. Anyone heard from Terry Tao? It's like, we have to hate him. He's like the smartest, nicest mathematician in the world. It's just awesome. Candace, Romberg, and Tao wrote this paper where they looked at this problem and they did kind of computer science style proof. Where they looked at under what conditions would this actually work. And what they defined is something called the restricted isometry property, which I'll show in a minute. It's not too important for this talk. But essentially what they said is, we can develop a proof with overwhelming probability, so it's like 99.999 forever, that the L1 norm will recover the L0 norm if certain conditions are met. One of those conditions is that the state vector is very, very sparse. So the bound that they have is something like, if you have a state vector that has 100 elements in it, we have a type of proof that guarantees recovery if you only want one element non-zero. So a super sparse state vector, really, really, really sparse. So that was interesting. They actually wrote a toolkit so that people could solve this problem too. They called it L1 magic because the fact that this works at all is pretty magical. I thought it was great that mathematicians were calling things magic. Things got more exciting. There was an absolutely amazing library written, and it's all open source by Vandenberg and Friedlander, who were at University of British Columbia now. I think Vandenberg's at UC Davis now. And they wrote the SPG1 LLI library, which that's what kicked things off seriously because everyone could solve problems very fast then. And then things got weird. And then things got really weird. So in 2009, there's an amazing paper published by Donahoe and Tanner. Donahoe's at Stanford, Tanner's now at Oxford, I believe. And what they defined in here is something called the Donahoe-Tanner phase transition. And it looks roughly like this. This plot takes a minute to describe, so I'll ask you to bear with me a little bit. On this axis here, we have how underdetermined the problem is. It's hard to see here, but there's a little 1 right here. 1 means the problem's even determined. The number of unknowns is equal to the number of data. Okay, we're good at solving that one, I hope. Well, to within a well-conditioned matrix, we're pretty good at solving this. And this axis here, what they show is how dense a state vector. So up here will be a fully dense state vector. That's a state vector populated by all interesting non-zero values. Down here is a state vector populated by nothing but zeros. So very sparse, very dense. And so what they did in this paper, and lots of people work on this nowadays, is they were able to take known problems that weren't of very high dimensionality, and then they know the solution. They absolutely know it. And then they tried to recover the solution using an L1 technique. And they tried it for various densities of state vectors. And what turned out to be really interesting is everything in this blue region here, they found out they could recover. The L1 recovery techniques recovered the L0 solution. Everything above this, in this red area here, it did not. So I don't know if I have another, yeah, beautiful. I have an even better slide that shows this. So this is the area in the Donohoe phase transition where L1 recovered L0. This is the area where it did not. And what turned out to be really, really interesting about this is for lots of practical cases, you turned out to be able to recover a state vector that's on the order of about 30% dense. This turns out to be really interesting. So if you have a state vector that has 100 elements in it, you can find 30 unique non-zero, let's say unique, or 30 non-zero elements. That's pretty cool. What's really interesting in the gap that people are still working to close is this is what we have theoretically, this is what we have empirically right now. So one of the themes that's really driving this type of research right now is empirically we find recovery conditions that are much, much better than we actually have theoretical guarantees for. And that's weird, but it's cool.
Just a quick question. So what is, I'm not quite sure what empirical means here. This is for like a chosen data generating process or across all data generating processes or like what, yeah.
So I'll say a little bit more about that. So it turns out that one of the things that matters a ton here is the structure of your linear operator.
Yeah.
And it matters a huge amount. And it does not work for every linear operator. So in this paper, they went through and they took, I don't know, it was thousands or millions of realizations of a Gaussian linear operator, of Poisson linear operator, uniform linear operator, and they derived sensitivity phase transition curves for each of those.
Okay, and then on the theoretical side, this is for across any linear operator, or?
I can't answer that question.
Okay.
I wish I could.
Okay.
I can't answer that. So the exact condition, the exact types of matrices that actually recover well were illustrated in a 2011 paper by Davenport, which I'll show a result from in a second. That's one of the key parts of this. One of the things that's so interesting here is people have tried to use compressed sensing in a lot of fields and failed. And one of the things that's come out of the empirical work is a highly well-conditioned matrix is not your friend here. A matrix that has a little bit of ill conditioning is actually incredibly useful. It helps throw a lot of stuff into the null space very, very quickly. And so one of the things we've been taught as numericists to do for a long time is to condition our matrices as well as we possibly can. But in the Davenport paper, they actually show that very well-conditioned matrices do not recover well with sparse recovery techniques. So your intuition just has to be thrown away for this. So this is the obvious next slide. Right? So I'm a geophysicist. I spend my time trying to predict earthquakes. To be upfront with you, I can't predict earthquakes. If I could, you would all know who I was. So nonetheless, we try to do this, and we try to do it in a cool way. So most people think about earthquakes and primarily in terms of the shaking that they cause, right? It causes all this shaking, that's bad. What I'm interested in is what happens when the earth isn't shaking. What I'm interested in is making measurements and predictions of what's going to happen during the interval in between earthquakes. And so the important physics here is that earthquakes are a byproduct of something else. Earthquakes are a byproduct of plate tectonics. Plate tectonics does not stop when earthquakes aren't happening. Plates continue to move. And in the last 20 years, we've started being able to measure how fast plates move. And we use things like this. This is a really fancy version of the mapping application in your phone. So when you're walking with your phone somewhere, it can tell you where you are, right? How does it do that? GPS. This is a very high precision GPS antenna. This is one in Japan. The GPS antenna is up here. This goes down about 3 meters into bedrock below it. Okay? And so with these very high precision GPS, we can actually measure motion that, with a precision of 1/10 of a millimeter per year. For some context, the fastest plate tectonic rates on Earth are about 20 centimeters per year. So we have tens of thousands of these across the Earth now, and the real revolution here is that we can actually measure the buildup of elastic strain that's going to lead to future earthquakes. It's the thing we've always wanted to see. So instead of studying earthquakes after the fact, we can study an earthquake before it happens. So that's what I spend most of my time doing. So this is an example of one from Notori City in Japan. Believe it or not, the destruction here was caused by the tsunami following the Great Earthquake. And this site was 2 kilometers from the coastline. The GPS station stayed up though, so that's kind of good. So what I'm going to show you here is kind of an iconic earth science or geophysics application into seeing into the Earth. Okay, so to do that, one of the things that some people are interested in is when an earthquake happens, they want to be able to say, what caused that earthquake? What part of the Earth, inside of the Earth, slipped and deformed and caused this earthquake? And so, to understand that, we have to think about where Japan is. And Japan is at the boundary between this big agglomeration of plates over here and the Pacific plate over here. The Pacific plate is an oceanic plate. Okay, really cool fact about Earth history. The oldest part of the ocean, the rocks that make up the ocean, are about 200 million years old. How old's the Earth?
4.6 billion?
About 4.6 billion years old. How weird is that? That the oldest parts of the ocean, which ocean rocks cover most of Earth, cover 2/3 of the Earth's surface once you take away the water, are only 200, the oldest parts are only 200 million years old. Why?
Maybe we're bad at counting how old the Earth is.
It turns out that the right answer is over here. We're very good at it. So what happens is oceanic crust is created in the middle of the oceans at mid-ocean ridges. When it's created, it's warm. As it cools, what happens? That is a positive coefficient of thermal expansion. So as it cools, it shrinks. It gets more dense. And eventually, after about 200 million years, it gets so dense that it starts to sink down into the Earth's mantle beneath it. So oceanic crust is continually created and destroyed. And in Japan today, this is one of the locations where oceanic crust, the Pacific Ocean, is sinking down into the Earth's mantle. So what we have is this boundary here between these large plates, and the Pacific plate is sinking down underneath Japan. Okay? It does so at a pretty shallow dip. It dips at about 10 degrees, so it doesn't plummet 90 degrees. It does so pretty shallowly. And it's this interface that generates most of the large earthquakes in Japan. You can imagine that this is not a very nice. Do you think rocks slide past each other very happily under great pressures? No, it's a mess. They're strongly frictionally coupled. So what we want to do is we want to figure out what parts of this interface is called the subduction zone interface, we want to figure out what parts of this interface ruptured during the earthquake. So before we do anything, we should do some resolution tests, right? Seems like a reasonable thing to do. Did we do resolution tests in statistics? Sometimes?
I don't think we call it that.
Yeah.
So.
By that name.
Okay, so what I mean is if we put in an input signal and then add some noise to that, can we recover the input signal using our estimation technique? What is that called in statistics? Okay, it's a thing we do. Okay, so I don't know. So one of the things we want to do is know if we can recover a signal that we actually know a priori. So we make up a signal and see if we can do it. So in this case, we imagine that there's this small patch here that slips uniformly at 30 meters. Cool fact about the earthquake, the peak slip during the Great Japan earthquake was 80 meters. So that fault slipped 80 meters in a matter of seconds. It's almost 1/10 of a kilometer. At the Earth's surface, the greatest manifestation of this that we saw was motion of about 4 meters because it's attenuated elastically through the Earth's elastic crust. Okay, so we take this input, we run it through a model. The model part is what I spend most of my life on, but not today. And then we ask, then we make predictions for what displacement should be at the Earth's surface. And then we turn the problem around and try to recover the input signal. Seems like a reasonable place to start. Okay, so the physics that we use for this, believe it or not, it's a shockingly exotic set of physics called linear elasticity, or just Hooke's law. It's a little complicated in 3 dimensions, but it turns out to be really interesting because it links up to your question about when does this work? What are the properties of the linear operator? So this paper by Davenport kind of brute force goes through about 12 different frequency distribution or probability distributions and assesses how well they can be recovered. And so for elasticity, for our particular model, we're somewhere between 2 n members in theory, but we roughly have this power law decay. Pardon me, what we're looking at here is the frequency distribution of the absolute value of the elements in the linear operator. That's the quantity that matters. What is the frequency distribution of those? And so Davenport showed that power laws somewhere around -2 tend to work pretty well, and it turns out that we get that almost for free from our physics. So we just got lucky, just totally lucky. Yeah.
Sorry, you lost me there for a second. I just want to make sure. So when you went back on the previous graph, you were showing that you can recover most of it, but there is decay that you have. And what you're modeling here is the basically the distribution that is that you end up creating.
Great question. Great question. So here, what I'm showing is for the linear operator that we have, what is the frequency distribution of the absolute values of the elements in that? So if you just take your linear operator, take the absolute value of everything, and then ask us, what's the frequency distribution of those things? What does that look like? And we get something that's approximately power law. Does that make some sense in terms of what it is? I haven't shown any recovery yet. I'm about to show recovery.
And what are the elements in the linear operator in your case here?
They're partial derivatives of these elastic displacement equations, which are these huge, ungodly complex Green's functions, which are gigantic. Does that help a little bit?
But I mean, presumably you have to do some sort of rounding in order to get this, because wouldn't you get very fractional? Aren't you going to end up with real numbers?
Yeah.
Okay, I'm glad to let someone else ask the question because I thought that implied a problem, but
Maybe it does. You could be right. I could be wrong.
seems unlikely.
Yeah. And I think that's the most likely explanation. So let me show you how this works. What we're going to do here is we reparameterize the problem in terms of the lasso algorithm, the lasso formulation that Tim Strauning liked. And then what we do is we exploit the Donahoe-Tanner phase transition to pick our one nuisance parameter in this problem. Nuisance parameter or tuning parameter is the nasty thing that a human usually chooses to make something look really pretty. So what we do here is the tuning parameter is called tau, and that controls roughly how dense of a sparse state vector you're going to try to recover. It's unfortunate that we look for what we now call the densest possible sparse state vector. We want dense and sparse. And so what we do is for our specific problem parameterization, we run it up to the densest one we can recover according to the Donahoe-Tanner phase transition.
Yeah, so in stats applications, the way that I've seen tau selected is via a cross-validation method.
Sure.
How does this differ from just doing repeated cross-validations to find kind of an optimal tau?
You want to know? I can't tell you theoretically. I don't know.
Okay.
In practice, it comes out pretty simple.
Okay. There we go.
So yeah, that's how we live most of our lives.
But there's also this sort of theoretical threshold for selecting.
Empirical threshold.
Okay, empirical threshold.
Empirical threshold. Here's an input. Here's recovery using a classic smooth technique. The reason, and you can see it kind of blurs out the input signal here, just as you expect. The reason it drops out here is we do something pretty reasonable. Well, I think it's reasonable. So the solution is 0 once it gets smaller than some threshold that no one would consider interesting. And the region up here is the region where we show that there's essentially no resolution. So anything in gray, you shouldn't believe anything there. All right, so that's what you get in the old world. This is what you get with sparse state recovery. And this is where you should ooh and ah, because that's pretty cool. So that's great. I've shown it with one distribution. Let's look at some others. This is probably the most dastardly slip distribution you can imagine. What if the earthquake didn't rupture a uniform patch, but ruptured a ring instead? So here, this is what you get using a classic L2 norm. And I would bet a lot of money that a regular human interpreting this, a human, not a statistician, a human, would interpret this as kind of one coherent blob that had some small local minimum somewhere. And then this is the type of thing you can recover with sparse data. And so why is this interesting? It's interesting not just as a mathematical exercise, but everything interesting in the Earth is an interface. It's the boundary between the atmosphere and rocks. Here, it's the boundary between the crust and mantle. It's the boundaries between different isotherms as you go down. These isotherms may be continuous, but once you cross certain threshold values, what happens? Rocks go through phase transitions. And so what we want to recover in almost every case is we want to find the edges of things. We know the bulk parameterization pretty darn well. It's the edges of things that have been interesting. And we just haven't been using the right imaging tool for a very long time to do that. And so that's what's really cool about this. So for this, there's a whole interpretation part of this, but I'm going to spare you that unless you're really interested in the mineralogy of subductions on rocks, which I'm guessing, no, okay. I'm guessing no. So I think that's what I wanted to say about compressed sensing. And now I have a neural network part if you want to hear that too. Anyone have any questions about this part first? I still can't answer your previous question.
Then I'll go for a new one.
All right.
So I want to ask maybe a sort of a philosophical question about this. So, I mean, when we're looking for these sparse solutions, right, you could either say that you're doing that because you believe that ultimately the world is sparse. There are a small set of things interacting, and I'm trying to recover that. Or you could say, well, at some level of complexity, I don't understand. Like if I have a fully dense matrix, or I mean, just I don't know how to interpret that, and so what I want to do is try and get to sort of the top 3 things I can explain about the world. And I'm just wondering, when you think about this technique, what do you know, where do you put your money? Which of those things are you?
Well, I have to say I'm pretty disappointed in you for reading ahead to my conclusion slide. So kind of heartbroken that we have to discuss that now. But the first thing to point out is we initially started this as kind of a very efficient way to detect edges. Turns out it wasn't the best way to detect edges. There's a related technique called total variation regularization, which has been in Photoshop for like 20 years. And so I took that stuff out of this because I wanted to move on. But you can also look for a state vector that is not sparse, but rather quantized. So a state vector that only has a certain number of unique values in it, but is densely populated. This turns out to be hugely useful in lots of applications, more useful than the sparse recovery technique in many cases. So we'll come back to the philosophy of this at the end, because essentially what I'll propose at the end is that this type of thing prompts a new way of thinking about what scientists should do with their time. Great question. Anything else about compressed?
Actually, I'm kind of curious about the model underlying this. So when we're trying to recover the parameters of that, so by parameters, I should think of blocks in that sort of space vector. How are you thinking about dependencies across those parameters within, given that this parameter is red for whatever signal you're trying to identify, what should I infer about parameters that are bordering it? Because it seems like we have these sharp lines, so I can't just infer, well, if one is red, then the one next to it might not be. But how, there seems to be some spatial dependence here that I think about.
Completely. So the linear operator has strong off-diagonal power. I think there's massive, absolutely massive covariance here. So the physics gives us that covariance, the exact form of the covariance.
I see. Okay, so we're using the physics to know the covariance matrix.
That's a great question. You can't just do one little piece.
Right, exactly, and you can't just assume that signals are independent conditional. Okay.
Not at all. It's painful. It's an ugly imaging problem. Okay, so now I'll talk a little bit about something else that's strange, perhaps even more strange. We'll see. I'm going to talk about using neural networks not to do anything with real data, but only to do something seemingly strange, only to help us with some of our HPC codes, our high-performance computing codes. So, as I said, one of the things that we try to do a lot is we try to predict where earthquakes will be, how large they'll be, and when they'll be. So, believe me or don't believe me, but we predicted the size and location of the Japan earthquake before it happened. It's published. You can believe me or don't not believe me, or you can read Loveless and Meade, 2010, Journal of Geophysical Research. cool, but we didn't say anything about when. Okay, so that's maybe not so cool. So you'd like to say something about when. So we spent a lot of time trying to develop techniques to do this, and we've now made our first prediction of when an earthquake will occur. Sadly, the answer is sometime between 2017 and 2032. This is for a large earthquake next to Istanbul. Hey, this is pretty good in the earthquake prediction business. So you say, that sounds great. You told me about one place where you did this. Shouldn't you do this with something that's not a sample size of 1? That would probably be a good idea. That evidently reduces your variance when you have more than one data point. Why haven't we? The reason we haven't is the computer simulations, the forward models that were required to do this, took 12.5 million CPU hours. It's a little bit expensive. And so that was running on roughly 2,000 cores for about 3 months straight. This is a dense HPC. It's got MPI communication everywhere. It is pain. It is real pain to do this. So we want to make that faster. Unfortunately, there are lots of nonlinearities here, and this is unpleasant. All the analytic thinking on Earth is only going to help you a little bit. So the basic idea that I'm going to talk about is how we can accelerate a forward model calculation by using a neural network. Essentially, we're going to train the neural network to learn our HPC code. That's the core idea here. And then it runs we can emulate it very, very quickly. Let me talk you through this a little bit. Okay, so here's the physics of the problem. I don't know if this will be of interest to anyone. The Earth, very roughly, yeah.
Well, what was the actual thing that took 3 months to run?
What's called a viscoelastic stress transfer calculation.
I see. So there wasn't that wasn't a machine learning problem.
No.
I see.
The machine learning problem runs
Yeah.
tolerably fast. I mean, you're done with that in, say, 3 hours training on 4 GPUs. It's a good point. Yeah, if it took longer to train than it did to run, you'd get a cool paper out of it, but you'd never use it. So, roughly speaking, the Earth looks like an onion. The Earth has an outer layer of the crust, then the mantle, then the core, then the inner core. Turns out there are lots of sublayers to these things. The layers that are cold, like the one we live on the crust, it's brittle, so it behaves almost entirely elastically. As you go deeper into the crust, temperatures and pressures increase, rocks behave more ductily, so they have a viscous component of deformation as well. So rocks behave in a way that's called viscoelastically. The common example that I have 2 daughters, and silly putty. If you have silly putty around your house, some people may. Silly putty is viscoelastic. Turn it into a ball, bounce it, it behaves elastically. Or if you turn it into a ball, leave it on a table for an hour, what happens to it? It turns into a puddle. It's a viscoelastic body. And actually, the Earth is slightly more complicated in terms of how it's viscoelastic, but that's the essential idea. So my former graduate student, well, my current graduate student, she's about to leave, Phoebe DeVries, she spent 4 years developing this HPC code that could solve these equations for the Earth efficiently. She did a tremendous job, and it parallelizes very efficiently. Downside is it's super, super, super slow, despite a lot of engineering that's gone into it. What does it actually look like? This is why it's cool. The key idea here, and this is the last thing I'll say about physics, the key idea here is that there's a time-dependent signal of where we are in an earthquake cycle. So the surface deformation of the Earth isn't steady in time. It varies in time as a result of this viscoelastic diffusion of stresses. And so this is really interesting to us because we can start to make observations of where we actually are in an individual earthquake cycle. And if you can say that, you might be able to say something about the time a future earthquake happens. So the basic idea is there's an earthquake in this upper layer here. We live right on top of this. The stresses are transferred everywhere on the Earth, and then they diffuse viscoelastically. As they diffuse viscoelastically, the crust and mantle are still coupled together, so the surface of the crust deforms in response to that. It's a cool little animation to show what that looks like. So I'm not going to explain all of this, but this one shows the coupling between the crust and mantle here, and you can see that everything's nice and continuous across it. And these variations here are the variations in surface velocities, which we can actually observe using our GPS data. It would take like 2 or 3 lectures to actually get through, how you actually do this. So it's got some nice colors. That's the important thing to take away. And it's really computationally expensive. So here's the basic idea. We're going to use a neural network to emulate our HPC code. In other words, we want the neural network to give us the answer that the HPC code would give us, but we don't want to run the HPC code every time because it's so expensive. And so what we do, typically we have a whole bunch of inputs that we want here, the geometry of our faults, what the viscosity of the Earth is. We have a whole set of other things like observation points, where's the earthquake, what's the geometry of the earthquake itself. Typically what we do is we run that through the viscoelastic calculation and we get some nice outputs. Displacements and stresses are typically the things that we want. Velocities we want to because we can test those against geodetic observations. So this is really computationally expensive. This is really interesting to try. Can we accelerate this in our region of interest using a neural network? So, I mean, probably everyone here does stuff like this on a daily basis. Basic idea, there's nothing exotic here, no LSTM, no CNN, no GAN. We just classic feed-forward network. So a bunch of inputs here, a bunch of outputs here. We train these just using standard backpropagation, nothing fancy. And the shape functions we use here are all very standard. We just alternate hyperbolic tans and rectified linear units. So this is a neural network circa maybe like 1988. This is not some blazing new one that's identifying our behaviors or anything like that. So it's really simple.
What is the ANN here? What is your acronym? Or what?
Oh, artificial neural network.
Oh, okay.
Yeah, I apologize. So this is the basic workflow for doing it. We evaluate the forward model a bunch of times, bin those into inputs and outputs, then do kind of standard back propagation with different batch sizes, test on an independent data set, and we turn the crank and see how well we do. So here's an example of the true solution. Here's recovery with an artificial neural network. Okay, it doesn't look that great, but it's actually not bad. The residuals are shown here, and you can see that as you add more training points, you do better and better and better.
How many layers of features did you actually have?
I'll show you I actually have a picture of the whole network.
Okay.
The fact that I say I have a picture of the whole network tells you how small it is.
Okay.
It's only about 8 layers deep, and one layer is 20 nodes wide, and the rest are only 10. Super, that's what's cool about this. It's small. The number of floating point calculations, which is why I'm doing this.
So it's the Y's in this calculation, you're using the results of having done the proper calculation? Okay, so you do it expensively once, and effectively you're creating your training set for the argument.
And so then the X here, you guys have just you've made these discretes, or what do the inputs look like in this case? Are they still reals or?
Yes.
Okay. Okay.
So here's what it looks like as it trains more, and you can see that the shape gets a little bit better in terms of how we represent that thing. So it starts to look pretty good, and this is the residual after training on 40,000 points. Residual is T. So not bad. All right, so I did that. It's amazing. We get this speed up of 1.5. That was a really good use of my graduate students' time and a lot of CPU time. Okay. That was for a really, really simple case where we didn't address most of the nonlinearities. So the case I just showed you is the purely elastic case where there's no time-dependent flow of the Earth's mantle. When we add time-dependent flow of the Earth's mantle, we train it in much the same way, and we get these interesting time-dependent patterns. Residuals is a function of time, and then this is the exciting part. It's not a speed up by 550%. It's 550 times faster. So this changes doing these calculations from huge data center calculations to workstation calculations, and in some cases, laptop calculations. And that is the message here. There are a lot of, just a second, there are a lot of complex calculations where if you know the parameter range that you're interested in, you can actually radically reduce the cost to evaluate things in that parameter range if you want to do that evaluation time and time and time again. You can reduce that radically. Yeah.
So if I understand well, the blue time is the time it takes to produce the data.
Mm-hmm. This is the time it takes to do 2 equivalent model runs.
Okay, and the red thing is to interpolate the data. To interpolate the data from these runs, or maybe I misunderstood.
So imagine you've trained everything already. You're completely done training everything.
Okay.
And then you say, all right, I want to calculate how this earthquake deforms the Earth as a function of time. To use the original HPC code, it takes that long.
So you have new initial conditions.
Yeah,
and
totally
everything.
new, totally new. And then this is how long it takes using the artificial neural network. So we're not the first people to invent this. There was a group at EPFL in Lausanne that did this for the Navier-Stokes equations, mostly for animation purposes. They presented this at SIGGRAPH in 2015. So I'd like to tell you, we had this brilliant idea. We saw what some smart people did. We said, hey, maybe that can solve our problem too. So now we're finally able to run a lot of these things and start to do many, 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 many more earthquakes. Yeah.
So presumably there has to be statistically we call this like some sort of random sampling idea here that the training data has to be, the test and the training data have to come from the same underlying distribution or something like that. So, and does the science or the physics of this allow you to kind of make that determination so that you know that when you go to run to use the neural network on a new set of data, you know that it's okay to use it on this data because the original VE code that you ran is sufficiently similar physically to this new system, or is that always going to be like an unknown assumption you have to make about when you use this method?
I think that's a great question. So the standard answer is that neural networks are a little more than very fancy interpolation schemes, right? Like, despite all the hype about them, that's really what they do. What we found in practice is that when we sample an area outside of our training area, if the variation in that area is small, so in the Earth, if we sample an area where the viscosities are higher than what we've trained on, there's not much happening there. So we actually get something that's pretty close to the correct answer. When we go to lower viscosity, where there's more variability, the neural network that's been trained is useless outside of the area that it's already sampled. Just completely useless.
Could you not get something like that also, let's say, with Gaussian processes or
Yes.
another interpolation? What's magic about neural nets?
Nothing. So people have done this with random forest. There's a group down at Duke. I don't know her name. Was a very good graduate student at Duke who's doing her PhD on using Gaussian process for this same thing. The group at Lausanne uses random forests. There's nothing unique about neural networks here, other than the toolkits are super, 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 super easy to use and really, really fast. So there's a bunch of ways to do this, and it has a name. It's it's HPC emulation, but it turns out it's really, really, really easy to do with modern machine learning toolkits. Yeah.
What did the sort of like cross-validation results?
Pardon?
Like cross-validation, or presumably there's some like validation of the network, not just it got an answer quickly, but it got the right answer.
Yeah.
Is that true? Did it get the right answer most of the time? Or-
Yeah. So that's what's shown in cartoon form here. This is a standard evolution of your loss as you add more and more data. So you start with very few data. You don't fit the data. You don't fit. The neural network does not fit the true model.
This is as it's learning though, right? This isn't like some validation on some held out set, right?
This is.
This is the
So this is
training process, right?
this is through the batch evaluation.
This is the change in the squared loss as it learns, right? That's what this is showing over like epochs in the training process.
That's a good question. I don't know if it's actually the training ones or if it's as Phoebe tested it against independent data. I don't know.
Yeah, because that's obviously like what
That's
you
a good
want.
question.
The response to Matt's question is like in some held out training set, we recovered X, Y, and Z, and those are not like features or those are not like places that were in the training data. Whereas this, based on the x-axis training points, looks like squared loss across epochs in the batch training process.
Yeah, that probably is because that's the standard workflow for
Exactly, yeah.
Keras, which we used on this test.
Yeah. But it's that would be, I mean that'd be the obvious thing to see, just some cross validation.
Yeah, works well. Yeah, like for Earth science, we're doing well. Earth science in order of magnitude agreement is considered spectacular. So this is what we can do. Someone asked about what the neural network actually looks like. I forget what. This is the complete neural network at the end. So here are our inputs. Here are 3 displacements, and then just a simple regularizing layer, softmax layer at the start, and then it's just alternating ReLUs and arctans through the rest of it. And that's it. You can see the whole darn thing. Nothing exotic at all. No memory, nothing weird. So it's really old school. It's just an old school thing to do, but it's really fast and changes the way we can do an awful lot of science.
What are the colors and the
They show the weights.
OS?
So
So it's like red is one extreme and paler, and then to blue is the other or something.
yeah, so blue is -1
Got
and
it.
red is +1. Yeah, it's not a lot of times you can visualize kind of all the numbers that comes out as something exotic. So these three types of machine learning I've talked about, or pardon me, three types of estimation. So I talked to you about this, and it was through some neat, kind of maybe boring applications. I don't know, perhaps boring applications. But it does raise some deep philosophical questions about what we should be doing with our time. And my point of view is that so much of science has been dedicated to creating a hypothesis and then spending your career fighting tooth and nail to defend that hypothesis, right or wrong, so that you can continue to get promoted. Does that sound like an academic career to anyone? But one of the things that's interesting here is maybe we're not that great at discerning. Maybe we're not even that great at creating. And so you can think about something like compressed sensing, not just as a way of reducing the number of coefficients in some domain problem, but you can think about it as a hypothesis selection tool. You could stack hypotheses together and then ask the question, what subset or combination of these hypotheses actually explain the data at a given level of resolution? There's a group, again, this group's from Rice, and they've been trying to do dynamical systems research this way. So they take big complicated sets of ODEs, like Volterra equations, predator-prey, something like that. And then what they do is they just stack all these hypotheses about what things could look like, cosines, products of all these terms, and then they sparsely recover them. And they've shown that even in the presence of a good amount of noise, they recover the Lorentz equations, which chaotic convection in the atmosphere, and things like that. So it's pretty cool. It says be creative, think about a lot of hypotheses, and maybe have the computer find the simplest subset, rather than us trying to determine what some parsimonious solution might be. Who says we're smart enough to do that? The other thing that's interesting and is a very hot idea these days, so forgive me if I'm being too fashionable, is what if we're not smart enough to create the hypotheses ourselves? So this is the field of what's now called interpretable neural networks. So neural networks are able to provide us with compact computational representations of, in some cases, very complex physics. So for the problem I talked about, it's the way we wrote the physics for the code is very understandable for the HPC problem. To someone like me. Like, we can write down what the terms are. There's 120 years of applied mathematics that help us understand that. But it turns out there are more computationally compact ways to do this. And what's interesting about that is the general idea that for problems of sufficient interest with sufficient nonlinearity, the ways that happen to be natural for us to parameterize a problem may be extremely inefficient. And it could be that there's a new role for scientists. And the new role for scientists, and statisticians too, is not to create the models anymore, but is rather to learn how to be interpreters of what these neural networks or sparse grids, whatever, Gaussian process, whatever you want it to be interpreters of what these things are learning, to be interpreters of these compact representations. Because throughout science, we've loved these compact parsimonious solutions, but I think we have to entertain the possibility that we may get to more compact ones faster, not by trying to figure them out from first principles ourselves, but by letting a computer figure them out through all the power that they have, and spending our time trying to interpret what they might possibly mean in terms of our physics or a statistical model or something like that. So that's the deep philosophy part, which probably sounds pretty crazy. But that's what I wanted to talk about today. I hope it was entertaining. I hope it was a little weird and not too boring. Thanks for your time.
Yeah, so I just want to like.
Did you find the error on slide 1?
No. But I'm simplifying this down to like in political science, like what would be the equivalent of everything you're doing in like the simplest possible case, which would be something like the difference between like a census and a sample. So it'd be like I want to learn, like this would be yeah, no, that's totally fair. So it's like if I want to learn about I want to learn the average average age of Americans in the United States, but it's very costly to run that through my HPC. And it's very costly to go out and actually ask everyone. So what I'll do instead is like a sample from the population and use my neural network on the sample, which just happens to be the mean, sample mean. And I'll get my best guess about the thing, so this is abstracting away a lot about, we happen to know through theoretically that this particular estimator is very good in this particular case, in the sense it's like the best possible. But I guess my question, but in order to be able to do that, in order to be able to make inferences about from my sample to the population, I need to have some assumption, some theoretical guidance about the relationship between those two things, and that requires some amount of science. And the computer can't, the neural network can't necessarily figure that out.
Well, that's part of the goal. So one of the things that, when it comes down to it, what neural networks are good at are learning unknown PDFs. That's what they're really, really good at. If you don't know the PDF, you can't parameterize it in any clever way. They're very good at determining that. And that's what all the rage about adversarial networks is these days. Like, they're so cool, I know. I feel bad about even saying it, but they're very good. They minimize the, what's it called, the Dubrecht-Leibniz convergence thing, and they're really good at that.
Yeah, I mean, I guess but in order at all, I mean, abstracting away from any particular neural network method or any particular machine learning method, right? You have to, it can't learn everything, right? There's some bound on what, there's always going to be some bound between some thing that has to be assumed about the model in order for it to be able to learn something, right? And so I guess this is what I'm just kind of like thinking about this part of it. I mean, in order for that bound to hold, the scientist needs to know what that bound is and be able to frame it in terms of the particular scientific problem that they're interested in, right? To some extent, this kind of, I'm just pushing back against this like fully automated science model that it seems like we're always, a scientist is always going to have to know exactly like how to relate, how to interpret these things. But in order to know how to interpret them, you have to be able to frame them in the larger kind of scientific inquiry. You have to know. Does that make sense? I don't know.
It makes a little, I mean, I think one of the things that's interesting about this whole discussion is the role of kind of our priors versus discovery. And I think one of the things that holds science back tremendously, this is especially the case in earth science, and it's in a lot of other physical sciences, is the belief that we have the right answer already. And
this is not a problem for social science.
It's a huge problem in science. So, do you know Naomi Oreskes here? Historian of science. She wrote an amazing book. She does a lot of environmental history, but she wrote an amazing book called The Rejection of Continental Drift. Now, who in this room thinks plate tectonics is a weird idea? No one. But the scientific community struggled mightily to accept plate tectonics. They accepted relativity and quantum mechanics, which truthier thinks those are weird. Yeah, they're a little weird, right? But the notion that the rocks beneath our feet moved, the scientific community struggled mightily to deal with. And it turns out that historically, there's roughly a 50-year lag time between when an idea is created and when it's accepted in the scientific community. And so one of the reasons I'm excited about this is if it takes the burden of creating the new idea off of the human. And I think that's interesting because I think so much, in the rejection of continental drift in particular, so much of the reason that new theories are rejected are because the right people didn't think them up. Let me say it another way. The cool kids don't like it when the non-cool kids come up with a cool idea. And I think this is a tool that helps force us to open the door because it's very reproducible. And I think it's a way for us to push forward in ways that are uncomfortable and hopefully strip away a little bit of the advocacy of the people coming up with the ideas. And that's one of the reasons I'm excited about it as a tool for changing kind of this idea that we need to wait for a great person to give their stamp of approval to an idea. So that's where I come from a lot on this. Yeah.
I mean, one of the things about neural nets is that so far they have been shown to be successful whenever there is supervised learning. And if you go a little bit beyond where you have taught them, I think they can predict and all that. But for unsupervised learning, I think there's many people, Poggio or other people who actually said that there is an issue that they have not been shown to perform well. So now to create a hypothesis, this implies full-blown, unsupervised learning,
I don't
correct?
think so. I mean, all you need to be able to do is define a set of inputs and outputs, and then a holdout set that you can test.
No, you will describe, I mean, if I write the gravitational law, the results of the gravitational law, I can find many ways to interpolate the data of the force between two planets. But the principle that this is a gravitational law that gives output to these planets, I worry if you cannot interpolate that, I think, without, let me go to the Lorentz 96 problem you mentioned. There's a parameter f there in the Lorentz 96, and if you keep f small, the system is behaving very smoothly. So we played with deep neural nets, LSTM, everything, and it works. You can predict a few steps ahead. If you increase the f to a chaotic system, everything fails. So it's as good as random guessing. So I don't know if that's one should be so optimistic that or would we not be wasting time browsing through whatever assumptions these guys are coming through? I mean, we're going to be wasting time to know.
Yeah, it's an interesting perspective, and it's the question of, do you want to waste time of throwing graduate students at a problem or throwing a computer at a problem? But I think there's an important rule of thumb here. Neural networks do not work well on random signals. Like that's known. Otherwise, the stock market would be over. But neural networks tend to work well in cases where a human knows how to, a properly trained human knows how to interpret the inputs, right? And things where humans can do a good job, that's where neural networks tend to do a good job. All I'm advocating for here is that we may be able to develop a tool that helps humans do that before they know how to do it. We may be able to deterministically attack a large range of data sets and start to build up the cases where it works and where it doesn't. And where it works, let's put a human on that so that they can start interpreting these things, instead of waiting for the human to say, I believe this is interpretable first. And I think that's a powerful way of looking at this. Yeah.
So I'm going to ask a practical question about when you showed the difference in time.
Did you say practical?
Crazy. So a lot of the revolution that has happened in neural nets happened because of the ability to port to GPUs, right? It was a really major moment. But when I looked at your differences in your graph, most of the time difference was not between running it on a normal computer and running it on a GPU. It was the change from your fully specified model to the
that's right.
neural net.
And
so
much fewer floating-point calculations required.
Yeah. And so I guess I'm wondering, what is that just? Is it that that the physics of the situation had led you to a bunch of basically complicated calculations, which gave you not much extra precision, and that's really what is the speed up here? Is that the right way to think about that, or is there something else going on that's more deep than that?
Yeah, I think that's a great question. The way I tend to think about it is this. These are incredible tools for essentially finding what I'll very loosely call, I'll use this terminology loosely, but very effective tools for finding basis functions that you wouldn't have otherwise thought of on your own. So maybe it's not Fourier, maybe it's not a wavelet of some sort. Maybe there's some wacky nonlinear combination. These are really good at finding compact representations of these things. And who knows? There may be somebody in applied mathematics in the 1800s who came up with something weird like this and gave it a name or something like that. But it's a great way of finding relatively simple functions that may not have names yet and may not have been studied in depth because of that. And that's what I think, what's going into these is not exotic, right? It's smooth curves, and there is the universality theorem, but that's almost never ever applicable because the width of the neural network required for that is just so enormous. But I think that's, again, falls into this creation category and this discovery category. What if there are, for a wide class of problems, similar weights and all sorts of things? Should this become the more fundamental representation of things? One of the things I think about sometimes, and if you didn't like my previous optimism, you're going to hate this. I wonder if in some ways we're close to an inflection point. So in Newton's Principia, you ever read Newton's Principia? really didn't have a lot of friends in high school, so that's like something that happened. So Newton wrote it after he invented calculus. How much differential calculus is in the Principia? None. Why? The language of the day was not differential calculus. It was not differential equations at all. It was Euclidean and Ptolemaic geometry. That is the language that's used to describe Newton's three laws, law of gravitation. It's all Ptolemaic geometry. And that was what was popular, or what was useful. After Newton, of course, after the French mathematicians, we saw the rise of differential equations as the primary currency of science for a very long time, and probably social science too. And so, in some ways, I wonder if we're at another inflection point where the primary currency of science, hold on, may not be PDEs or ODEs that we know how to interpret readily, but maybe a network or sparse grid representation of something because it's so computationally compact. What if that becomes the primary language that we use to describe things? And the question then is, how do they map to ODEs or PDEs or something like that? And as crazy as that sounds, I mean, it's important to remember that we already went through this transition when we went from geometry to calculus, essentially. Nobody in this room, I don't think, could derive, much less understand, even the simplest arguments in Newton's Principia. Not because they're exotic, but not because they're difficult, but because they're in a language we completely don't understand, which was the standard for 1,700 years. And we've transitioned to ODEs and PDEs, but I'm not convinced that's the end. I'm not convinced we're done. And I think we have to consider the possibility that these more compact computational representations of things may become primary rather than, right now they're criticized as black boxes and we don't really understand. And when I hear I don't understand, that's something I'm excited about. Like, that's what I want to spend my time on. I don't want to spend my time on it. I understand it. Like, that seems silly. So philosophically, I think there's a lot at stake here. I don't know which way it's going to go, but I think it would be silly not to pay attention to a lot of this. This is fun. I just riff on all these ideas.
Can I ask you another question? I mean,
All right.
Since I'm playing the skeptic here. So you showed all this history of compressive sensing, etc., right? So what was nice in the recent years is that finally we have proofs about when it works, when it doesn't work, and the same thing applies with many things in mathematics, that you have a proof, and then if your code doesn't work and you don't get second-order convergence, go look for the bug, right? Now, do you expect that a neural net will be able to come up with a hypothesis? Let's say I give you that, there will be a hypothesis. But who's going to do the proof, which is the essential aspect? Who's going to give you guarantees that this is correct or this is not correct? Will it be another neural net, or
So
how do you see that?
that's a great question. So in science, there's this famous saying that anywhere a scientist goes, a mathematician has been 200 years before. I think that situation is changing rapidly right now. I think we are changing kind of the ordering of things from mathematicians going there first. Perhaps they've been there already, but it's not clear where there is. Because I think empirically we're going places that mathematicians don't understand very well right now. And so I think the ordering in which these things are done is uncertain. And that's interesting. So we also have to accept we don't have to accept the idea. We have to consider the idea that if this ordering is reversed in some ways, we may end up with something, could be a 200-year lag time between when we empirically show something seems to be pretty useful and then when we have the proof that it works. And I think that's a very weird world that intellectuals and academics may have to run into. The lag times may become very, very long and in the opposite direction to what we're used to. So that's really uncomfortable because we may be without guarantees for a very long time if we get them at all. But it's what the new world looks like, and it's interesting. Of course, we could have one brilliant person who changes all that tomorrow, but neural networks have resisted. I mean, the big problem is they're not convex. Non-convex things are wicked, wicked, wicked hard. So like you just lose 99% of your mathematical arsenal when you give up convexity. And so the number of tools available is just so small to actually attack these things. worrisome, but we may have to just learn to live with it.
Okay, thank you so much.